of Europe, I bid good afternoon. To the people of the Americas, I bid good morning. To those joining us from Asia, I wish you a pleasant evening. And finally, to the chair for today's session, would you please do us the honor of introducing the first speaker?
All right. Thank you very much, Professor Bohr. Yes, I'm very happy to introduce the first speaker of today's session. It's Yvonne Geyer. She's going to tell us about superstring loop amplitudes from field theory. And I think we can start. So go ahead, Yvonne.
Yeah, thank you so much. And let me also thank all the organizers for putting together the conference and for this amazing introduction, and giving me the opportunity to present some work, some joint work with Ricardo Square, Ricardo Montero, and Ricardo Stark-Munchau on superstring loop amplitudes from the field theory limit. And maybe just to set the stage for you, let me remind you of the respective status of these two theories, of loop amplitudes in these two theories. So in the superstring, and let me, for concreteness, just focus on the 4-particle amplitudes, although there has been tremendous progress recently by Eric Doka and friends on deriving higher point amplitudes, and for massless external states, there's been very early progress at 3-level and 1 loop in the 80s, but then it took almost 20 years for the impressive calculations, say by Doka and Fong in the RNS context at 2 loops. And since then, really, there's been only partial results, despite heroic calculations, both on the Cairo measure and on a certain low energy limit. In contrast to this, in supergravity, for 4 points of maximal supersymmetry, the state of the art is 5 loops. And this is despite having started basically at the same point as the superstring, following directly from this calculation in the 80s. So there's an immense discrepancy between these two theories. And so the goal of today's talk is to at least partially try to rectify this and to import some of the supergravity advances that we've seen in recent years into the superstring. Now, we're going to try to do this only at 3 loops. And what we're going to rely on heavily is basically mostly 2 modern amplitudes techniques. Neither of them will come as a surprise to you. The first of them being the color kinematics duality, which is very obvious because this is the main tool that has been used to drive these supergravity results. And the second tool that we're going to use are worldsheet models for field theory. And that should also be very intuitive because this is going to be the method that will help us make some contact between supergravity and the superstring. Now, to just give you a vague outline of where we're going to end up and what we're going to try to be doing, our strategy in the end will be the following. What we're going to start out with is a supergravity integrand in the color kinematic or BCJ representation. And what we're going to be spending the first half or so of the talk on is to find out how we can rewrite this in a form that is more reminiscent of string theory on a worldsheet. In this case, we'll first lift it to a nodal sphere, and this will heavily rely on worldsheet methods for field theories, and in particular, the Ambitwistor string and amplitude formulas that come out of this one. And then in a last step, we're going to see whether we can uplift this using symmetry constraints to a higher genus formula and use experience gained from the Ambitwistor string versus the superstring at lower loop order to find out what the string, or to arrive at a proposal for the 3-loop 4-point superstring amplitude. Okay, so most of our time at first will be spent on the Ambitwistor string and the corresponding amplitude formulations, but I'll pay particular focus on how it ties into the BCJ formulations at loop level. Okay, so let's dive straight into this. Our main tool for lifting the BCJ representation that give us the loop results to the superstring will be the world-lead models for field theory, and in particular, what is going to be useful for us is the so-called Ambitwistor string. Now, we won't need many details for this, but let me just briefly introduce you to it. So this is just a chiral world-lead theory. And while there are many different models that I've abbreviated here by just including some additional matter action SM, what we're particularly going to use is the RNS model, which is so-called for the close analogy to the RNS superstring, has two fermion systems here, psi1 and psi2. But let me highlight that both of these are chiral. Now, why is this a model for field theory? We can gain a first intuition from this by looking at what the target space of this model is. And as you can see from the action that I've written, even from just the bosonic part, is that it maps into, well, P and X, both with Minkowski indices here, modulo P square equals 0. So this maps us to the phase space of complexified null geodesics, which is also known as Ambitwistor space, hence the name. And we can see that this gives us a very good intuition that this might be a very suitable model for describing massless field theories. In fact, we can make this precise by looking at what the spectrum is. And indeed, we find that for the RNS model that I had on the last slide, the spectrum is directly type 2 supergravity. And so this justifies that I've called it a world-lead theory for quantum field, for QFT amplitudes. Now, the upshot that we're going to be spend the next few minutes on filling in the details is that correlators in these theories correspond to field theory amplitudes, or more precisely for higher genus and higher loop contributions to, we should understand this as the field theory integrands. And just to give you a flavor of this, how this goes, let us first look at the simplest case, which is tree level. In this case, we'll just put n of these vertex operators, of which I've given you the rough structure up here, and calculate the correlator when we're on a Riemann sphere. Now, the first thing to notice that comes out, which is just because this is a world-lead model, is an integral over the moduli space m naught n of Riemann surfaces with n marked points, which I've written here, modulo the usual Möbius invariance. Now, this is already quite reminiscent of the string, obviously, because both of these are world-lead theories. However, this is really a model for field theories. And the way that this is reflected in the amplitude formulas is that this actually localizes on a set of constraints, which are known as the scattering equations. Just to give you a flavor of how this comes about, the PX system, the main bosonic system, actually has a very simple dependence in these vertex operators. You can see that the only X dependence sits in these exponentials, which is also true for the integrated vertex operators that I haven't written here. This means that it's actually very straightforward to integrate out the PX system. And what you find is that P just localizes onto its equation of motion, written here, which is very simple to solve at tree level. We just find that P is meromorphic, the sum over Ki sigma minus sigma I, and because P is a one form with a corresponding d sigma. But now remember, in the action, we actually gauge the P square constraint. This is what told us that we're actually looking at massless particles. Whereas when we're squaring this very firmly looks non-zero. And how this is resolved is that if you're careful about the quantization of this constraint, you get precisely this localization on the delta functions that impose that the residues at all the marked points, sigma I of P square vanish, which in turn then is enough to guarantee that P square will be 0 everywhere on the Riemann sphere. Now, this amplitude formulation that we've derived here is known as the CHY amplitude after Cachasso, He, and Yuan in 2013. And so we have already seen that two of the crucial features, namely that it's an integral over the moduli space, but completely localized on the scattering equations. And let me just maybe highlight 2 points here. While what comes out of the models will be something that is valid in a critical dimension, the formulas that I'm writing here are actually valid in an arbitrary dimension. And the second point that I'd like to make is how you should read these equations. Is you should always look at the momenta ki as given, ki square being null, and we're solving for the sigma. So this is completely localizing this integration here. Now this part is actually universal for any massless field theory. You can prove that this is always, any amplitude can be written in this way. And what specifies the theory, which will be, is this, it's also called an integrand, a worksheet integrand, if you want, IN. Now we'll be mainly focusing on two theories today, which is going to be Young-Mills and gravity. And for Young-Mills and gravity, it turns out that these integrands have a particularly simple form. You can already see here the structure that I've tried to highlight with my color coding is very much one of a worldsheet double copy. So we have the Young-Mills as the kinematic times a color factor, and the gravity as two kinematic factors. Now, per se, this is all we could hope for. This is already beautiful. But for our talk, we will actually want to be a little bit more precise on how it relates to the kinematic space formulation of the double copy, which I've, for the audience, obviously, there's no need to review this, but just to set the notation, which I've pinned up here. And how to do this is the following. These kinematic and color factors that we've seen on the last slide have a very nice representation as sums over Park-Taylor factors, which are just these cyclic differences of the sigmas, where we should think of these with the two endpoints, one at n fixed, and we should think of these as corresponding to half-ladder master diagrams. For the following reason, the numerators that sit up here, the color and the n here, are in fact precisely the color and the BCJ numerators that appear in the kinematic color kinematics double copy relations. Okay, so much for tree level. I hope you've gained a bit of an intuition from this. Let's actually look what happens at higher loop order and what type of formulas come out. Now, in principle, it's very clear what should be done here. You just repeat the same calculation on a higher genus surface. And in the way I've said this, it should hopefully be clear that there's a huge amount of work and a huge amount of detail here. I've cited some of the papers up here. But the main point is that this can be made precise and calculated up to 2 loops. And what we find is the following. As expected, you find an integral over the moduli space, MGN. And there's, in fact, up to 3 loops, a very nice way of parameterizing this, which is as follows. So on any Riemann surface up to 3 loops, we pick a homology basis of A and B cycles. And then we normalize our holomorphic differentials omega I, out of which there's G on the genus G Riemann surface, against the A cycles. And then the integrals over the B cycles of the holomorphic differentials will give us the period matrix, which is a very nice way to parameterize up to 3 loops the moduli space MGN. Now, to decode for you the other objects that are appearing here, note that in the correlator, when we now solve, we can repeat the same calculation for the px system, which again tells us that p is localized on the same equations of motion. But when we solve this now, we should actually use the Green's function corresponding to the higher genus curve. So in that case, this will just be a meromorphic differential with residue plus minus 1 at the mark point zi, and this is just a reference point. Now, the other new feature is that at higher genus, the solution to this equation actually has a homogeneous solution, omega I, that is proportional to the holomorphic differentials, where the corresponding zero mode, I've called here L to already indicate that this is the loop, that this will play the role of the loop momentum. And we should integrate out over this, so I've put this up here in the formula. Now, then the last bit that we need to decode before we actually do the hard part of the integrand is to look at what the scattering equations become. And remember, the scattering equations will always enforce that p square is 0. This is the constraint we gauged in the model. And what we can see is that there's n scattering equation that do exactly the same as a tree level, that they just set the residues at the marked points to 0. However, at higher genus, this is not sufficient to set p square completely to 0, which is very simple to see, just because p square is proportional to omega I, omega j. So accounting for this, we then have more parameters that will in general be complicated functions of the loop momenta and the marked points, and the remaining scattering equations set precisely these u's to 0. Now, just to take a step back and have a look at this in a little bit more detail, there's two important properties that I want to highlight for you here. First of all, this is modular invariant if you correctly include the loop momentum here. And second, if you look at just the part that is the loop integrand, this is completely localized again on the scattering equation, which is very simple to count. Just look at the dimension of the moduli space mgn versus the number of scattering equations, both of which are n plus 3g minus 3. Now, let me also say, this is if we remember what our general strategy is, this is actually quite reminiscent of superstring amplitudes already, and we'll see that in more detail later. So that's good, but on the other hand, this is quite far from field theory as we know it. So at this point, it's certainly far from obvious how we would lift, say, the BCJ numerators and the usual BCJ representation of the integrand at higher loop order to something like this. For example, it's not even clear that this is well defined in 10 dimensions. Calculating anything with this is really hard. Remember, the scattering equations will now involve complicated meromorphic differentials at higher genus. It's not clear how to cope with this. So the good news is it is straightforward how to do this. And the reason is the following. These amplitudes actually can be shown that they simplify drastically using a residue theorem on the moduli space. Now this goes as follows, and we'll look at this for the simplest case where there's no subtleties or anything, which is just the torus. So on the torus, what I've drawn for you here are the solutions to the last scattering equations, u equals 0, on the support of all the other scattering equations. So in particular, any one of these points, we should be summing over that value for tau, and it corresponds to a torus like this. Now, since this is completely localized and we're just summing over the solutions here, we can actually perform a residue theorem on this fundamental domain and pick up whatever other poles the integrand has on that fundamental domain. Now, it turns out that the integral actually only has a single pole in all of this, and that pole sits at tau equals I infinity, or it's often going to be useful to use the variable q at q equals 0. But on that particular point in the moduli space, the torus actually degenerates. This is a boundary divisor, and we find instead a nodal sphere, just a sphere with two additional marked points that I'm going to be calling plus and minus that are identified. Now, because this is important, let me spell it out for you in detail also at the level of the formulas. So here I've written the integrand at one loop as an integral over the moduli space m1n. I've just kept the integration measure d tau and the delta function in u. Remember this new scattering equations. And I've just put everything else into a new function I1 of q here. Now, the residue theorem tells us that we can just strip off the delta bar here and pick up whatever other poles there are, which is in particular the pole at q equals 0 that I've spelled out here, and then any other poles in this integrand here, of which there are none. So this whole integral is actually equal to what we've written here, delta bar q. And if we simplify this, obviously, so the moduli space here is what we've seen before, is just the moduli space m naught n plus 2 of these nodal spheres. And the 1 over u simplifies to 1 over L squared. Now, I've spelled this out for you at one loop, but we've seen over the last few years that this can also be done at least at 2 loops as well. So up to 2 loops, we can think of a nodal expansion instead, as the loop expansion instead as a nodal expansion instead of a genus expansion. And just to give you a feeling for what the corresponding formulas look like. So remember, first we traded the localization on p square equals 0 for this localization on some of the modular parameters, the diagonal ones in the period matrix qii equals 0. So first of all, that puts us on the moduli space of m naught n and now g nodes, so meaning 2g new marked points. And we pick out the overall, the factor of 1 over Li squared that sits out front here. Now, I'm giving you here the details, but we actually won't need the details. What I want you to focus on is the structure. So we find that there's an additional contribution to this IL and IR. These are just what you would come out directly at Q equals 0. But we also find a Jacobian contribution from the integral over the modular parameters Qij, mapping this to the marked points sigma I plus minus of the nodes on the sphere. And the two stars here are just as a health warning. This is supposed to be interpreted only on the torus. You have to be a bit careful with the rigid translation. So this is only true in a suitable sense that this comes out directly of the formulas here, but there's no subtlety for higher loop order. Now, the other new feature that you might not expect, especially from tree level, is that there's a new function sitting here that is just a function of the nodal points, and it's first non-trivial at 2 loops. And this is a remnant of the fact that we integrated the modular parameters Qij for I smaller than j here over the fundamental domain, and we should really map that to a full Riemann sphere integral afterwards. Now, last but not least, this is again localized on some scattering equations. And remember, we traded the localization on p square equals 0, so p square is non-zero anymore by now. But these will still include a constraint, which I've called curly p here. And this is going to be setting p square equal to some combination of the loop momenta and what used to be the holomorphic differentials on the higher genus Riemann surface, and now have simple poles at the nodes. Now, just a few comments, and I'll be brief here. First of all, this is really useful because it allows us now to interpret these formulas in dimensional reduction for d smaller or equal than 10. And we'll also see on the next slide that this allows us to write down super Yang-Mills formulas as well as supergravity. Now, the other point that I would briefly like to make is that this is an unorthodox integrand representation that we land on, where everything that involves, every propagator that involves only one power of the loop momenta comes in this linear form. However, we won't talk about this much because it's related to the standard representation in a very straightforward way by a residue theorem. So to be precise, it's easy to go from the standard representation to this linear representation. And instead of spelling this out in detail, let me just sketch for you what this looks like in a particularly simple example of a massive bubble here, where I've started out with the standard representation and then just used a partial fraction identity, which is the simplest incarnation of this residue theorem. And then the type of representation that we're actually going to land on is obtained by shifting the loop momentum in each of these terms such that there's an overall factor of 1 over L square. And you can see that we find precisely these type of linear propagator factors that I wrote up there. The only reason I'm mentioning it right now is that this actually gives us a very nice physical interpretation of what the scattering equations look like, and also this function CG, which is namely that this function P precisely encodes for us that only the correct type of poles appear, and C tells us that there are no further unphysical poles. Now, this is going to be something very useful in lifting this to genus 3, but we won't actually discuss this in detail here. Feel free to ask if you're interested in more details. Now, for us, the main reason why this nodal sphere representation is immensely useful is that it allows us to make very direct contact with the BCJ double copy in kinematic space. at G loops. Now, let me just remind you, this is the BCJ double copies at the level of the integrand. And the beauty is that on the nodal sphere now, we can mimic precisely the relations that we found at tree level, meaning in particular that the super Young-Mills integrands are obtained by a single copy. So let me remind you, this was the supergravity ones, and we just substitute one color factor here, where these color and kinematic half integrands are again given by sum over these Park-Taylor factors that correspond to half-ladder master diagrams. And in particular, both the color and the numerator factors here are BCJ numerators for these half-ladder masters. Okay, so far, I actually haven't said anything about superstring amplitudes. So far, we've only talked about field theory. So what we've seen so far is that supergravity can be written in two representations, one's on the genus 2 and one's on the nodal sphere, and or any also for G equals 1. And let me now specify that we're going to just look at 4-point amplitudes. So what I've done is I've pulled out a factor r to the 4 here that is proportional to the tree level amplitude. And then I've just renamed the integrands into y, which is standard notation. And what we've seen is that the one on the nodal sphere allows us to make very direct contact with the BCJ representation, whereas we've said that the higher loop one, the higher genus one, sorry, is more reminiscent of the string, superstring. And so the question is, can we make this precise? And just to contrast the two for you right now, let me write down the type 2 superstring amplitude in the chiral splitting formulation here. So you can see that we also have this integral over mg4, and I've introduced the chiral splitting parameter. I've called them L here to highlight the relation with the standard chiral splitting factor here and the Kober-Nielsen factor up front. Now, there's obviously important differences, but what I want us to focus on is these factors YA, Y, and YS. It turns out, if you compare this at 1 and 2 loops, that there exist representations such that that YS and YA for the superstring and the Ambitwistor string are the same. Now, the tilde here is meant as a health warning that on the superstring, what we mean by this is that we pick this representation up to terms that integrate to 0 and on a specific super gauge slice. And the important bit is that this representation is actually independent of alpha prime. On the Ambitwistor side, this is only true up to things that vanish, contributions that vanish on the scattering equations. Now, in fact, we can say something stronger. We can precisely identify what this representation is for which this is true. And the direct equality is true for the BCJ representation out of all possible representations. What do I mean by this? The BCJ representation is the one where I take the Ambitwistor one, restrict to the nodal sphere without using the support of the scattering equations. And there is just a direct equality between the Jacobian and the Y that comes out of this, and the BCJ representation, by which I mean the sum over the BCJ numerators over the Park-Taylor factors. Now, this observation too is really what we want to be using to make contact afterwards from the Ambitwistor string to the string. Okay, so this is a good point to issue some health warnings, assumptions that we're going to be making. Now, we are going to assume that the string, superstring, and Ambitwistor string representations that we had on the last slide remain true at genus 3 from now on. Now, this is an assumption, and especially if you went to higher genus, this is something you would need to revisit, because it is known that for G equals 4, for both the string and the Ambitwistor string, you'd run into the Schottky problem, which is something you would have to address. Also, at the latest at G equals 5, you'd run into the non-projectiveness of the supermoduli space. And also for G equals 4, there's new features in the scattering equations that you'd have to investigate more carefully. Moreover, we're going to assume that this observation too also extends straightforwardly to G equals 3. So under these assumptions, we can now fill in the outline that we saw at the beginning to the following strategy to go from field theory to a superstring 3-loop proposal. So in particular, we're going to start with the supergravity loop integrand in a BCJ representation, and then translate this to the worldsheet, by which I mean the nodal sphere, in this case, the 3-nodal sphere, using the observation, the BCJ relation that we had before. And then we're going to use our, well, we're first going to uplift this to try to uplift this to a higher genus case by writing a modular invariant ansatz and demanding that our higher genus expression matches the nodal sphere in the nodal limit. And then we're going to use our observation 2 to identify this with a string. Okay, so this is a highly non-trivial procedure in general. So just as a proof of concept, let's look at a case where we know the answer and see how this will play out. Let me point out that this is already highly non-trivial. This is what took Eric Doker and Fong 20 years after the first 1-loop results to calculate in 2005, and 6 papers. Okay, so the upshot is going to be that applying this strategy at 2 loops reproduces their results for the 2-loop YS factor. Now, we're going to start out with our numerator representation. In this case, the numerators, I've pulled out the factor of R4. And the numerators in this case are just simple. They're just simple Mandelstam's. And I've not given all of them here, but all of them have the important feature that there's always 2 between the 2 plus and 2 minus 2 external particles. We can then translate it to the nodal sphere using our relation between the BCJ numerators and the nodal sphere. And then the difficult step in general is to write down an ansatz that has the correct modular weight, but also has enough degrees of freedom. However, at 2 loops, first of all, because we know the answer and also because the answer is quite simple comparatively, this is actually easy to do because we know that it has to have modular weight 2. And there is a very obvious object of modular weight 1 that is also happens to have the correct form degree, which is the delta, which at any loop order is the determinant of these holomorphic differentials omega and marked points z, where these degenerate, let me remind you, to the nodal sphere just as the omega I plus I minus, the ones that have simple poles at the nodal points. Now, writing an ansatz with all of these, we find immediately the correct result. So you can see that this is quite simple. It's just a product over 2 deltas with the correct factors of Mandelstam's out front. However, especially because this is so simple, it is actually a good idea to pause at this point and see some of the details of how we would actually try to write this down if we didn't know the answer, or at least pretend we didn't. Now, first of all, it's clear that both of these objects, YS and YA, have to have modular weight -2. And I've given you here the counting it's quite easy to do for any genus G. Moreover, they have to be homology invariant, meaning if we take a mark point I and move it around any of the cycles, it has to be invariant, and it has to have the correct form degree in the Zi, which is actually a really important point. Now, ideally, we'd want a complete classification of this object, some functional basis, so that we can just go ahead, write down a sum of all terms in this functional basis, and then fix the coefficients. Unfortunately, such a classification, to the best of our knowledge, does not exist. So the best we can do is we can write down an ansatz that is consistent with these properties using every object that is defined at higher genus that we can find. Now, the first of these that we've already seen are these deltas at any G that have modular weight -1, and they will be really important tools for us also at 3 loops. There has been a complete classification of the ring of modular forms. I've listed them here for you. And in particular, the psi10 is really important also in the superstring, where it features in the chiral measure. So in particular, we might want to include something like the typical terms that come out of the RNS superstring, where this is just, which look as follows. We have the chiral measure and we have the Zego kernels, which are just the 2-point functions for the fermions in the RNS superstring. And for the amplitudes, what we find typically is a sum over all spin structures with the chiral measure, as well as cyclic products of these Sego kernels. Now these vanish, these cyclic products, for n smaller or equal than 3, and for 4 points we have two of these cyclic products that we can possibly have. Hence the tilde, there's just a numerical factor here. But we see that neither of these actually give us any new information at 2 loops, because they're just expressible in terms of these deltas. So then at 2 loops, what we would do is just write down an ansatz in terms of these deltas, meromorphic differentials, and these modular forms, fix all the coefficients, and indeed we are left with our G = 2 result that matches the superstring result by Doka and Font. Now, with keeping in mind what we've learned here, let's now try to apply this actually to something where the answer is not known, which is the 3-loop integrand, both for the Ambitwistor string and the superstring.
Yvonne,
now the
you have 5 more minutes before questions. Yeah.
Thank you. Now, the easy part of this is actually the BZJ representation, where I say easy because the hard work has been done by, among others, Henrik. I've included the pretty picture here from their paper. And let me just maybe highlight one of these terms. So the one of the numerators that would contribute to this is a half ladder if you follow the solid line here. And the first lesson we should take away from this is that we expect now terms that are numerators that are linear in the loop momentum, and also therefore the integrand y to be linear in the loop momentum. We can then translate this to the nodal sphere as usual, and note that we need the factor J3 here to identify the Y3. Now, the J3 we can luckily just calculate from the usual relations, and there's a factor here that is not very surprising. This is just products of Jacobians that look like the 2-loop ones. However, there is one factor that I want to highlight for you, which is this J hyperelliptic here, that comes out in the numerator, and which carries the subscript here, because it's reminiscent or strongly tied to the hyperelliptic locus on higher genus on genus 3 Riemann surfaces. Now, in general, for a genus G, the genus 3 Riemann surface, the hyperelliptic locus is given by psi9 = 0, where psi9 is one of the modular forms, of the root of one of the modular forms at genus 3. And that J hyperelliptic comes out precisely in the nodal limit of this psi9 factor. Why is this important for us? Because we can study what, well, the integrand looks like on J hyperelliptic just by looking what the right-hand side of this does. And we find that it is actually non-zero. What this tells us is that this Y on the nodal sphere has to contain a corresponding factor of 1 over this Jacobian. And in particular, this tells us that the higher genus string or Ambitwistor string integrands contain a factor of 1 over psi9, which ties in very nicely with some of the proposals for the chiral measure. Okay, so the difficult part, the last step of this, how do we lift this to higher genus? Now, what I've written here is just a very general form of the ansatz, which should be understood as the following. So first of all, this has to have modular weight -1. It has to be a 1 form in all the marked points. And we want it to have the correct nodal sphere limit. In particular, this means that it's linear in the loop momentum, which I've already encoded here, and also that in the hyperelliptic, that to leading order in the hyperelliptic limit, this has to be 1 over psi9, has to have a term that goes as 1 over psi9. Now, again, there's no complete classification of such objects, even ignoring the last point. So the best we can do is write down an ansatz that includes everything that is known in the literature. And there's, in particular, 3 important objects, all three of which we've already met at genus 2, one of which is the delta. Then there's the full ring of modular forms, which now has 34 generators and was classified by Suyamine in the 80s. And last but not least, there is a chiral measure proposal by Cacciatori, Dalla Piazza, and Van Gemen that now looks like this chi8 factor over psi9, precisely the psi9 that we found already, that plays such an important role in the hyperelliptic case. Of course, we have the meromorphic differentials to account for the form degree. And so writing down everything that is possibly consistent with the first 2 points of our requirements here, we end up with the following results. Now, let me go through this in turn. The yi here is just the term that is linear in the loop momentum. And the alphas are just some kinematic coefficients that can indeed just be fixed by symmetry requirements. The omegas are again our holomorphic differentials, and we can see that these deltas, as expected, play an important role here. They also play an important role in one of the terms in the part that doesn't depend on the loop momentum, where we have a factor of just the meromorphic differentials up front. Yeah, and I've written this in a way that makes a lot of symmetry properties manifest, of interchanging 1 and 2 in this case. The most difficult term is this S, which is meant to remind you of Sego kernels. And this is now a sum over all 36 even spin structures with the chiral measure and both types of cyclic structures that the Sego kernels can have with the correct prefactors here. Now, since this is a big result, let me maybe just have some comments on this. By construction, this is modular invariant, and we've constructed it such that the field theory limit, at least for the nodal sphere, matches what we constructed from BCJ. It also has another important property that it must have. It is homology invariant, which was nicely discussed by Eric Doka and friends in the two-loop case. What this means is just we can move a marked point around a B cycle, and it should be invariant under this. And this is actually quite non-trivial. So there's a cancellation between this factor that is linear in the loop momentum, and you can see that this transforms the loop momentum itself. And so there's some cancellation with this B factor here. The S is invariant by itself. Now, you might also wonder about the consistency with the low energy limit, the impressive calculation by Umberto and Carlos, where they showed that this matches the expectations from S duality. And it's easy to see that this agrees with the term that is linear in the loop momentum, but a detailed comparison we're currently working on. Okay, just to wrap up, maybe let me end with some important questions. Now, it's not clear how you would simplify this. This is something we haven't been able to do. And this all ties back to whether there is a functional basis which we can use to write these things. I should mention the RNS origin of the measure that enters into this S factor is far from clear, but we're not thinking of this as coming directly from the string here. We're really just using this as a tool in writing down an ansatz that has the correct modular properties. And let me highlight that an understanding of our classification of these objects would also be really important to be able to say anything about the uniqueness of this proposal. Okay, and since I think I'm a bit out of time, let me just end with the Outlook slide and say thank you very much for your attention.
Thank you very much, Yvonne. It's a beautiful talk. Let's see if there's any questions. Yeah, there's a question from David.
Yes, thank you for this overview. My question is really a matter of epistemology. Do you think that string theory is sufficiently well defined at present that there exists an amplitude at more than 3 loops, or that it actually lacks sufficient definition to define one in principle?
I mean, at more than 3 loops, I would say that is already more than ambitious. I think we've seen that already at 3 loops, the obstacles are quite severe. At 3 loops, I think these can possibly be overcome, but it is a good point that you're raising, that there might not even be a good enough understanding of the string theory itself to make any statement about more than 3 loops, which I've certainly, which is why I've been very quiet about higher loop anything.
Thank you.
All right, I guess I had a question related to David's questions. So you call this a proposal. So what would it take to prove it? I mean, what's the missing steps in a proof?
Okay, so note that we've only made statements about sort of field theory and consistency here. So we haven't actually attempted any superstring calculation. The superstring calculations are prohibitively difficult. Let me just remind you, I think I had this on one of the slides. There's a sum over 36 even spin structures. These are just the even spin structures in the RNS. You might try to do it with the pure spinor superstring instead, but yeah, I defer questions to how difficult that is to Carlos and Umberto. We've thought about that quite a bit. So on the superstring side, this is certainly hard to do. On our side, I think even for stronger evidence, there's a few steps that you would need to we would like to fill in. So, for example, for the maybe here is already a good point to look. So for the lift here, we've used a lot of properties that, I mean, for a physicist, we've done it to a physicist's level of proof, but maybe for a mathematician, this is not at the level of a proof. And then for the uplift, remember, there is no complete functional basis for the ansatz that we're writing, so we cannot claim uniqueness right now. Obviously, this has the correct limits, so and it has a lot of the correct properties, but as long as we can't prove uniqueness and there's not a complete basis, there's not even a proof that this is unique. So I think those are sort of my 2 answers for what would need to be filled in, either directly from the superstring side, which is very hard, or at least better evidence towards uniqueness of the proposal, and also some details on the steps that I think should be filled in.
How hard is it to come up with a functional basis? Do you have
hard?
It's hard.
Hard. Hard. So maybe just to highlight this, there is already this ring of modular forms, with the 34 generators. I don't know how Selina wrote these down. Even just calculating them in the nodal limit for us is hard. There is millions of terms in each of these. This is not a simple thing, and these are the modular forms. We really were interested in 1 forms with the correct modular properties, and not just the 1 form, but carrying 4 of these form degrees. It's already at lower loop order. This is hard to classify, let alone at 3 loops.
All right, I see Paolo has a question, so let's do that one, and then we have a break.
I mean, do I understand correctly that you can write spin structure by spin structure or not?
No, sorry. So most of this has been written in a way where we think of the sum over spin structures as already performed. If you let me go back to the 2-loop result, there it's maybe very obvious that what comes out of this, well, naturally, because we're writing down an ansatz that is of the form where we've already performed the sum over spin structures. The reason we have terms that have the sum over spin structures explicit here is that our ansatz without these terms is not broad enough. So you can see that in the full answer, we have a mix of terms where we think of the sum over spin structures as already being done, and terms where there's some leftover sum over spin structures that just needs to be done because we don't know what they should be simplifying to.
So you cannot write the expression for a single spin structure.
We haven't tried. I mean,
No.
if there was concrete interest in this, we'd have to write down a different ansatz. So we'd have to structure this a little bit differently. The ansatz we've been writing right now in terms of these deltas and the ring of modular forms is naturally in the form where this has already been done. If you wanted something that is a direct expression with a sum over spin structures, you'd have to instead include both the term that is the S here, and some terms that look more like what you would typically find in the RNS model, where you have a sum over the Zego kernels and additional punctures that come from picture changing operators and factors that come from the chiral partition functions. It looks very messy. I'm not sure, and we haven't done this, is maybe the best way to say this.
Thank you.
Okay, I think it's time for the break. So let's have a 10-minute break, and we start again at the hour. And if anybody has questions, they can. All right, thanks, Yvonne, for a very nice talk.
Yeah, thank you.
I guess I had one more question. So can you do the same thing at for loops?
Okay, so, and I just unshared, but yeah, so there's, as you well know, everything gets an order more difficult at every order of loops that you add. And so this is true here, I think, at every step, except for at the step where we just take your results. Mm-hmm. So already translating this to the Riemann, to a nodal Riemann sphere, everything that I've brushed under the rug here comes back to haunt you of how do you write the scattering equations, how do you write the function c there. We know how to write the scattering equations, but there's new aspects. So the function c is not that you need to write is not as simple anymore. And moreover, it's not clear to me that such a function exists without additional constraints on the integrands that just have to be true that I don't know how to implement at this point. I haven't thought about much. So this is at a very early stage. Mm-hmm. And then if you try to lift this to higher genus, you have to address the Schottky problem. You have to now find a good basis with all of this implicit. And remember, as long as we don't have a better understanding of this S, already here, this was 36 even spin structures. That was already a bit of a challenge. And so currently we're doing these calculations in Mathematica, and there's a lot of issues with square roots that you need to be really careful with in these definitions. So doing this with more spin structures sounds difficult. So the summary is, it's probably as much more difficult as you would expect it to be, and I don't have much to say on it.
Right. Thanks.
But also, in principle, there is a way to attack the problem, and there's also no abstraction that makes us think this is not possible.
That is a good point. So the strategy is meant to, I mean, we have formulated it as a strategy rather than as a concrete application, because in principle, there's no obstruction to doing this. The same holds, by the way, for, say, two-loop higher points. The only difficulty is always you need to write down an intelligent ansatz for the higher genus one. But in principle, the same could be done, say, at higher points, or, yeah, as long as you don't run into a concrete obstruction. In principle, it is a strategy for higher loop orders.
Mm-hmm. I mean, the reason why I was asking the question about spin structure is that in 88, we wrote a paper in which we present the spin structure of the only Navier-Schwarz spin structure for an arbitrary number of loops in superstring. Yeah. And so if you know the expression for the only Navier-Schwarz particle going into the loop, one can compare with the result of that paper.
But you need all the even spin structures, though, and some of them will be, some will be NS-NS, but others will be NS-Ramon, and others will be Ramon-Ramon.
No, but if you can isolate only the spin structure in which you have Navier-Schwarz going into the loop.
Yeah, no, I see your point. Yeah, not in the way we've written it, but if we had it in a way that was, if we found an equivalent expression with manifestly just where each spin structure, where it's manifest per spin structure, we could directly compare it to yours. That is a very good point. Thank you.
I try to find this paper and I write the reference on the chat.
Thank you.
I forgot now.
So if I could just ask a little bit more, there was a comment on chat by Chris Krylova talking about mathematical obstacles beyond genus 3. Now, I've heard of the Riemann-Schottky problem. I don't understand it, but mathematicians have difficulties characterizing Jacobians of curves and Riemann manifolds. That seems to me a sort of practical obstacle. It means we don't know how to do something. But right, and it's clearly, so I'm not asking the practicality of solving it, but is there a belief in the community that string theory is sufficiently well defined as an operational procedure, that there is a unique ansatz? It's just very complicated and we don't have enough mathematics to write it down. I mean, do you believe that, Paolo?
I mean, I think they're working on it. So currently it's up to genus to 2 for symplectic manifolds. I mean, there are obviously efforts to do it for higher genus. I'm not really that involved in the field to be able to tell you what the problems are and how far they've come, but there's definitely progress in that area.
Well, there is a lot of progress even in the non-perturbative parts, because, you know, this is the loop expansion, but there are non-perturbative contributions which string dualities then constrain, and they then constrain the relation between those non-perturbative part and the perturbative part. So, you know, the pieces of the puzzle do not indicate that there's a problem of principle, but how you prescribe the calculation of the loop amplitudes, say in the RNS string or in the pure spinor string, then are obstacles that are, but those are believed to be technical obstacles. For instance, Yvonne mentioned the issue of non-projectedness of supermoduli space. This means that the relation to the ordinary moduli space is not clear. So in those integrals that Yvonne showed, there was integration of the period matrix that's already in bosonic moduli space. So somehow, how do you get there from the supermoduli space? And this is then presumably becoming much more complicated at higher loops. But so that was also motivation for this work, because the question is, if these prescriptions are so complicated, then maybe there must be another way of calculating the amplitude, just as it is done also in field theory, that somehow goes in a completely different way. And then maybe that also informs what those prescriptions should be, if people, you know, develop those first principle formalisms, constructive formalisms better.
I think I have to interrupt now, so we need to prepare for the next talks.
Thank you very much.
Thank you. Is Yael here? Maybe you want to share your slides to check if it works.